In this class we're going to talk about decision criteria under uncertainty. Now, from other classes you'll know that decisions may be made under conditions of risk. That's where we have some idea of the probability of the future outcomes. The risks may be assessed objectively or subjectively. But we can also make decisions under uncertainty. Now, uncertainty, we have no idea. Uncertainty is making decisions when we have no idea of what the future holds. So it's the most difficult type of decision making. Uncertainty, we have no indication of what's likely to happen. However, to clarify the way in which decisions are made, economists and philosophers and psychologists and lots of disciplines have come together to try and see how decisions can be made under these conditions, and that's what we're going to look at here. So we're going to start with a table. Now this is a somewhat unusual table. I'll explain what it means. I'll put the cursor onto the screen. Here we have outcomes along here. Outcome 1, outcome 2, outcome 3, outcome 4. And here we have the alternatives. These are our decisions. We can make decision A or decision B or C or D. So in our case we have 4 decisions here. And also, coincidentally, we have 4 outcomes. Each one of these outcomes may be called a state of nature. And by that we mean it's what confronts us. We don't know which one's going to arise. We don't know what's going to happen tomorrow. So this may happen, or this may happen. In many cases in business, when decisions are made over a long period of time, perhaps over years, in the context of, let's say, investment, decisions have to be made with very little knowledge of the future. In fact, arguably no knowledge of the future. They are just decisions. So the future may be very good, which could be our state of nature 1. It could be not too good, state of nature 2. It could be fairly bad, really, state of nature 3. State of nature 4 could be terrible. So I've just assigned interpretations to these, but they are what we call states of nature. They're what may arise in the future. We don't know which one will arise. It could be this one, or it could be this one. We don't know. What we do know is we have 4 decisions to make. We must pick our decision from these 4. Now, under these conditions, we have sets of rules that can help us at least clarify the way we think about decision making. So as I said, the outcomes are known as states of nature. If you choose, let's say, alternative C, and the state of nature is O2, outcome O2, then we would get 4, whatever 4 is. It could be profits in the future, 4 million or whatever. But we get 4. And we'll say 4 is good and 0 is not too good. 4 is better than 3. So if we choose C, and if the state of nature was O2, then we'd have an outcome of 4. Okay. The 4 is known as a payoff. This is a payoff. That's the term we use to describe what is the outcome. The outcome is a payoff. And this is sometimes known as a matrix of payoffs. A matrix of payoffs. A collection of numbers which represents the various payoffs under different decisions and different outcomes. So that's our matrix of payoffs. So if you choose D, and the state of nature is O1, then we will get 1. And the payoff here is 1. So that's the appropriate payoff. It's D and O1, which is 1. Now, the problem with this analysis. Well, with uncertainty, we have no knowledge of the future, and therefore we would not know the figures in the matrix. So we would not know the payoffs. This is a major problem with this type of analysis. Where do we get these figures? We've got a matrix of payoffs here. We have 2, 2, 0, 1, 1, 1, 1, 1, 0, 4, 0, 0, and so on. Where do we get these? If the future is unknown, how do we know what this matrix of payoffs is? And that's a major criticism of this work. So it's not something we can use in practice. What this will do is it'll tell us more about ourselves, the way we make decisions, than about how to use this to make the best decision, because we don't simply have these figures. So that's the major criticism. So let's look at some rules at how we make decisions. This is more, as I said, to do with us and the way we make decisions. So let's look at the first one. The first one is called a maxi-min. A maxi-min approach to decision making under uncertainty. So we avoid the worst and select the maximum of the minima. And I realize that sounds horrendous. We avoid the worst. Okay, we avoid the worst situations. We select the maximum of the minima. It's known as a very conservative approach to decision making. It's a very risk-averse sort approach to decision making. It assumes no interdependence between the outcomes. They're all independent. And I talked about down here in the parentheses, in the brackets, games versus states of nature, not games versus opponents and states of nature. So this is a game, sometimes described as a game against nature. These are the outcomes from nature into the future, and this is a game against nature. In other words, these outcomes are not going to reconfigure themselves to hurt us. It's not like playing against a person. A person may have strategies to beat us. If we play chess with someone, they've got a strategy to beat us. So it's an active game. This is a passive game. We make the decision and the game does not alter. These figures do not alter because we've selected A or selected B or whatever. This game is passive. It's a game against nature. So there are two types of games we can play. This one is called a game against nature. It's passive. If we select alternative B, those are the outcomes. And they don't change because we've selected B. But if this was a game of chess and we selected a particular strategy, the opponent may change his or her strategy to counter ours. That's called an active game. We'll talk about game theory in a separate class later. The criticism of the maxi-min approach is, why do we assume the worst? States of nature are not always hostile. So we always assume the worst in this one. It's a maxi-min approach. And I'll show you what maxi-min is in the next slide. But for the moment, it always assumes the worst. And that's not necessarily true. So how do we work it out? Well, first of all, we maxi-min. We calculate the minima. Now look across here. For, say, decision A, the minimum is a 0. This one here. So there it is. That's the minimum. For the next one, the minimum is 1. They're all 1s, so that's a 1. It's the minimum. The next one, C, the minimum is 0. And the next one is, the minimum is, for D, the minimum is 0. These two here are 0, so that's a 0. So these are the minima. And then the rule tells us to maximin. Take the maximum of the minima. And the maximum of the minima is B. So with this set of figures and with this decision rule, maximin decision rule, and this set of figures, we would select the alternative B. But of course, that is conservative, because if we selected A, we have a chance here of getting 2, an even bigger payoff. But there again, we have a chance of getting nothing as well. If we selected C, we have a chance of getting a 4, but we've also got 3 chances of getting nothing, so it may be risky. So the maximin is to maximize the minima, and it is conservative, but that's the rule that gives us that particular one. There are other rules. I mean, a maximax. Now this is really aimed at the optimist, or if you like, the gambler, the person who likes to take a chance. So it's for the so-called plunger, the person who likes to gamble. If other states of nature occur, then the gambler will get nothing. So this is a high-risk strategy. And the maximax is calculated in similar fashion to the maximin. This time we take the maxima, we go across the same set of figures, and we go across and we say 2. 2 is the biggest number here, so 2 is the maximum. Here it's 1, they're all 1s. Here it's 4, and here it's 3. On this line here, 3. So these are the maxima. And then we maximize the maxima. So we take the biggest of these, which is 4. So we select C. Well, as you can see, it really is for the gambler, because we have 3 chances of getting nothing here. If outcome 1, 3 or 4 happens, we get nothing. It's only if outcome 2 happens we get the 4. So a maximax approach to decision making really typifies the gambler, the person who likes to take a lot of risk. Here's another one. It's called the regret criterion. It's based on the work of a famous quantitative worker in the area called Savage. It's called the regret criterion, and it really focuses in on what's known as the opportunity cost of making the wrong decision. It looks at the penalty for making the wrong decision. So here's our table again. Now we look at the best outcomes for each, the best payoff, I should say, for each outcome. Well, the best payoff here is 2. The best payoff here is 4. There it is there with C. C and O2 gives us a 4. So that's the best outcome or payoff there. For outcome 3, the best payoff is 1. And for outcome 4, the best payoff is 1. It's either this one or the next one. It's either A or B. So now we've got the best outcomes. So we've considered for each state of nature, we've considered the best outcomes. Now we develop another matrix based on what we've got here. And what we do simply is we say, here's the best one. Here's the best outcome for this. So let's subtract each number from this one and see what we get. So with outcome 1, 2 minus 2 is 0. 1 minus 2 is 1. 2 minus 0 is 2, and 2 minus 1 is 1. So what this matrix down here has done is it's given us a comparison against the best outcomes. So if outcome 1 comes about and we have decision A, we have no regret. If it's B, we have a regret of 1, because 2 is the best one, so we must have a regret of 1. We could have got 2. Down here we could have had a regret, sorry, down here we have a regret of 2, because we get nothing. We could have had 2. We actually get nothing, so our regret is 2. And the final one, we have a regret of 1. We could have had, the best one was 2, we would get 1, so we have a regret of 1. 2 minus 1, which is 1. Now, what we do is we choose the minimax of the regrets. The minimax of the regrets. So we look at the maximum regrets and we choose the lesser of these. Well, the maximum for A would have been 2 if I'd written it down here. Looking across, that's the maximum for alternative A. The maximum regret is 2. The maximum regret for B would be 3. The maximum regret for C is 2. The maximum regret for D is 1. So minimax of the regrets tells us to take the minimum of the numbers here, which would be a 2, a 3, a 2 and a 1. And the minimum of that is this one, D. So that's quite a popular way of looking at decision making, to try to minimize the regret of making a wrong decision. Now let's look at something called the Laplace principle, and this is called the principle of insufficient reason. It suggests that choosing a strategy which is optimal in a situation where the opponent chooses all strategies with equal probabilities. So, according to Laplace, the best that we can do under uncertainty is to behave as under risk, where all the strategies of the opponents might appear with equal probability. So, Laplace assigns a probability to each one, a probability of an outcome. So let's have a look at it. Here's our table again on the top. Now, what happens here is we simply add up these numbers and take the average. It's the same as giving each of the numbers an equal weight. So we just simply add these up. We get 5 and take an average. 5 divided by 4, there are 4 outcomes possible. 5 divided by 4 is 1 1/4. And here we add these up. We've got 1, 2, 3, 4 divided by 4, which is a 1. Here we've got 0, 4, 0, 0 divided by 4, which is a 1. 1, 3, 0, 0 divided by 4 is a 1. So on this rule, to take the maximum of these numbers would suggest we should select A. Now what Laplace was suggesting here was that we simply don't know the future, so all states of nature should have the same probability. All outcomes should have the same probability. Each one has, there are 4 outcomes, so each one has a value of 1/4. And we take the likely outcomes, the payoffs, under each one and multiply it by its probability. So we'd multiply that by a quarter, that by a quarter, that by a quarter, and so on. Add them up and we get 1 1/4. So we maximize by taking just the average of this one across, the average, the average, the average, and gives us this figure here. Now let's look at the Harvick decision making. This is we weight the outcome of the worst and the best. We take the best and the worst and we place a weight on them. Here's our table again, the simple table. Now what Harvick was suggesting was we weight the weighted average of minimum and maximum payoffs. So let's say the weight we assign to the minimum payoff is alpha. Alpha is somewhere in the region between 0 and 1. The weight of the maximum payoffs is 1 minus alpha. Now if, just for ease of calculation, let's say we take alpha is equal to 1/2, then we have equal weights. Now, if we go across here, we take, let's say, decision A. Well, the worst that can happen is 0, and the best that can happen is a payoff of 2, which can either arise here with outcome 1 or outcome 2. So that's the worst, outcome 3, that's the best. So we take 1/2 times 0 plus 1/2 times 2, which is equal to 1. For B, it's 1, 1, 1, 1. So we take 1/2 of 1 plus 1/2 of 1, which is equal to 1. For C, we take 1/2 of 0, because these are the worst outcomes, plus 1/2 of 4. It gives us an outcome of 2. Sorry, it gives us a figure of 2. And the last one is a 1 and a 3, so it's 1/2 times 1 plus 1/2 times 3, which is 1 1/2. We select the largest here, so we'd select C. So what it is a weighted average of the worst and the best outcomes. In our case, we've picked simple weights. We've taken both weights to be the same as 1/2. But you could change this. You could make this a quarter and make this would then become 3/4. 1 minus a quarter. The value of the weights you choose will reflect your propensity to risk. So if you like risk, then this one you would give more weight to this one here, the maximum payoffs. If you're more conservative, you might put more weight on the alpha. Well, the criticism of this is that it concentrates on the extreme items. And also, how are the weights determined? As I said, there may be a characteristic of the decision maker. And if alpha is greater than 1/2, then the person is pessimistic. So it's an extreme case. It looks at the maximum and the minimum and takes a weighted average of those. And that's the Harvick solution to decision making. So in this class, what have we looked at? Well, we've looked at what's known as games against nature. We have looked at the payoff matrix. We said that the payoff matrix is just a set of figures. Given we can't see the future, we don't know what the payoff matrix is. So really what we're doing here is not looking at actual decisions. We're looking at how people make decisions. What sort of people are there? There are people who like Maximin, people who are Maximax. There are people who take a weighted average in Harvick, or people who simply don't know and they go with the Laplace solution. So it's really telling us something about the decision making, the decision maker, and the decision making that the decision maker uses. But it doesn't really tell us anything about how to help us make decisions itself, because the figures don't exist. It is uncertainty, and we are confronted by pure ignorance. We don't know what the future is, so we can't make that decision. So that's all I want to deal with in this session, is to look at how decisions are made and what sort of decision makers there are. Maximax, Maximin, Harvick, Laplace, whatever. So that's what we've done. And that concludes this video, so thank you for watching.